Okay, let's make a start. Let's have a look at exponential form. So we've done one form. So you shut up. We've done rectangular form, okay, of complex numbers. Then we did the polar form. Remember, in order to use De Moivre's theorem, we have to have it in polar form, okay. Another format is exponential form. And you might argue, well, why do I have to learn another third format for writing the same complex number? So, 2 plus j2 can be written in rectangular form 2 plus j2, or it could be written in polar form, root, square root, or whatever, 8, or whatever it is, okay, angle pi over 4, or exponential form, which is the one we're going to discuss now. I'll tell you why in a second, why you want to write an exponential form. There's one great advantage this has over the other two. So what we're going to do is convert from polar to exponential, or rectangular to exponential, and then vice versa, from exponential to rectangular or to polar. And we'll look at some examples as well. The important thing here, like I said to you in the first hour, that's why I worked in radians, is that the argument theta has got to be in radians. It cannot be in degrees anymore, okay? The argument theta has got to be in radians. You've got to work in radians now. You've got no choice. The last section, like I said, look at the book. I've done in degrees. I did my notes in radians, but you could flip-flop between the two. It wouldn't have made any difference. Here you can't. You've got to work in radians. You've got no choice. Okay, and what this says is r theta is equal to r e to the j theta, where theta must be in radians. Theta must be in radians. Okay, theta must be in radians. Okay, let's do an example. Let me doesn't work, does it? Okay. All right, let's do this example then. Let's do, I'm going to zoom into some of this. Convert 2 cos 60 degrees plus j sine 60 degrees into exponential form. So how do we convert this into exponential form? I want to convert that into exponential form. Okay, I want to write this as r e to the j theta, yeah? So how do I write this as r e to the j theta, yeah?
Well, you've got r equaling 2 already.
Yeah, of course, r is easy. R is 2. What about theta?
Is that 60?
No, it can't be 60. Why can't it be 60?
Oh, so you need to change it into radians.
Let's ask someone, why can't it be 60? Yeah, you've got to convert it to radians, yeah? Okay. So you go right there, 60 degrees, of course. What is that in radians? Yeah, pi over 3, exactly. This is pi over 3, okay? So this is equal to, okay, this is equal to 2 e to the j, what? Pi over 3, of course. This is equal to 2. So you write that as 2e to the j pi over 3. Okay? Now, of course, like I said to you, that what advantage is there of using, of using exponential form? There must be an advantage. There's no point, me telling you, okay, it's on the syllabus, or I get paid to teach you to do this. That's why we're doing it. That's not good enough. I know some academics, only 7 weeks ago, and someone asked him, why are you teaching this? Because he goes, I get paid to teach this. That might not be a good enough answer for you. And if you said that to me, I would agree with you. I've said to you from day one, you should give me a bloody hard time. You pay this university a lot of money. You worked out it's 50. I said to the student, the physics rep worked out £50 a lecture, and he goes, no, it's 60. I goes, she said it's 50, 50ish or 55, whatever. So you should give me a hard time by all means. Okay, but so why is this on the syllabus? Why is this format, this exponential form? You might say, well, I've got rectangular form, I've got, polar form. Why do I need another format? Why bother? What's the advantage? I'll tell you the disadvantage. The thing I wouldn't want to use exponential form is if I wrote that, you don't know what that looks like, do you? You've got to think about it, you've got to work it out, put it in rectangular form and then draw it, okay? You know, well, there's 260 degrees, so I can have an idea, fair enough. But still, you know, if you saw, 2 plus J1, you would know exactly where it is. So, what about this? What do you think the advantage of this? Go ahead.
Well, what if you command J to the J?
Yeah, that's another one. That's a good J. Yes, if you want to work out what J to the J is, it's much better done in exponential form. You're right, much easier in exponential form. Some things, are easier in exponential form. There's one other advantage. I'll tell you one thing, some things are easier in exponential form. That's definitely true. Yeah. You could do logarithms. Anything else? Okay, is there anything else? You can solve equations like, cos z is equal to 2. Well, let's not worry about that one so much. The great advantage is you don't have to remember any special rules. All you do is, if you want to multiply two matrices, you use the rules of indices, which you already know from algebra. If you want to take it to the power, you don't have to remember de Moivre's theorem. All you do is take RE to the, if you want to work out RE to the j theta to the power n, the way you would normally use the rules of indices, R to the n, e to the j n theta, yeah? Okay? It's not, like in polar form or rectangular form, whatever. You can remember special, you don't. The advantage is, you want to divide two complex numbers, you don't have to work out the, if you want to divide two complex numbers, say R1 e to the j theta, okay? R2 e to the, say you want R2 e to the j beta, guess what that's going to be? Yep.
It's going to be R1 divided by R2.
Of course, your R1 divided by R2.
You've got E to J theta.
Yeah.
Minus J.
Yeah, minus beta. Yeah. Okay, you're using the rules of indices, yeah? Using the rules of indices. That's what you have to do. Those rules you already know. So instead of trying to remember the complex conjugate, working out the complex conjugate, multiply the numerator and denominator by the complex conjugate, squaring up the denominator, no. Two complex numbers, you've got them in polar form, all you do is, nothing to remember. You know these rules. If you had this in algebra, it was x1 plus, e to the, 5 divided by x2 e to the 7. You would do exactly what we just done there. Yeah. You know those rules. You know how to apply those rules. Rules of indices is all you apply. So that's a good advantage of exponential form. No special rules to remember. Okay. Thing you've got to remember about exponential form, it's got to be in the argument's got to be in radians. Okay. So, like I say, the disadvantage is here. Let's have a look at this one. Convert this into e to the 2 plus j pi over 4. Convert that into rectangular form, a plus jb. Why would you want to convert that into polar form? Into rectangular form, sorry. What advantage is there? There's not mathematics. Yeah, go on. Yeah, I can draw it. I don't even know what that looks like. I've got a clue. I can think about it and do a bit of working out. So I know what it looks like now. Okay. And I think because the pi, I think it's on the leading diagonal. I think it's on the diagonal. Okay. But I can't prove that. Okay. So once I can put it into a plus jb form, then I know exactly what it looks like. I know which quadrant it lies in and everything else, don't I? Well, how do I convert this into rectangular form? What's e squared plus j pi over 4? What is that? Sorry?
E squared times e.
Yeah, exactly. The rules of indices, a to the m, a to the m plus n is a to the m times a to the n. You know that, don't you? Those rules of indices, you've done that millions of times since you was 13, 14 or whatever. So here, all you do, that is going to be e squared e to the j pi over 4. Okay? Well, e to the squared is e to the squared. E squared is e squared. What e j to the pi over 4? What's that? Let me go back and remind you. This is what it is. You got the r bit. This was e squared, yeah? This was e squared. Okay? What about e to the j theta? How do we write that? What does this thing here mean? What does that mean? Sorry? Yeah, so what does it mean? You put it in rectangular form. What does it mean?
Does it just mean that theta is like the angle?
It's an angle, yeah. What does it mean? You could go back to. You can't just forget everything we did last week, you know. This thing. Sorry. What? Cos. I think you said the right thing. You have to have the confidence to say it. If you're wrong, it doesn't matter. This r theta, I must remind you again, r theta, if you go back to last week, what we did r theta, remember, r theta was r cos theta plus j sine theta. That's what it was. Like, you've got to remember this. You've really got to remember that. That's one formula. I mean, I don't recommend remember a lot of formulae, but you've got to remember that. You've got no choice. Okay? So e squared, e to the j pi over 4, e squared is your r, so e squared, what do we get? You tell me. Yeah, cos pi over 4, yeah? Cos pi over 4 plus, yeah, j sine pi over 4, yeah? Got j sine pi over 4. Cos pi over 4, work it out on your calculator or whatever, you should know this one really. E squared, that is 1 over root 2 plus j sine 1 over root 2. Remember, at 45 degrees, the cosine and sine graphs cross each other, don't they? Okay? What would you do? What could you do with that? Yeah, 1 over root, take the 1 over root 2 out, yeah? So it's e squared over root 2, 1 plus j. So now I know exactly what it looks like because I know it's on the lead on the diagonal, doesn't it? Not really diagonal, couldn't make sure it's on the diagonal, 1 plus j. We know it's got this length, e squared over root 2, which you can work out whatever that comes to in decimal format, okay? So that's that one done. Okay, so you can convert. I think for that, I don't know why you were confused, but you've got to remember r theta, this thing here, that's what you've got to remember. R theta means r cos theta plus j sine theta. You've got to remember that. You know, no way could you do this. If you don't know that, you couldn't do this question. You know, how would you put it into rectangular form? I don't understand. You just can't do it. Okay, so you've got to remember that. You've got no choice over that. Okay, so show that e to the j theta is equal to cos theta plus j sine theta. How do we show this then? How would you show this? R is 1, yeah, exactly. So we'll substitute r is equal to 1 into r e to the j theta gives, you know, gives our result. So e to the j theta is equal to that, isn't it? Yeah? Simple as that. I've talked about, I've talked about Gauss in the first hour, okay? Perhaps the most prolific mathematician, maybe not the greatest, definitely the top 5 and not the top 3, is Euler, Swiss mathematician, 1707 to 1783. And I'm sure I told the math students this. He, like I said, 48 years after his death, you know, St. Petersburg Academy was still publishing papers by him. That's how prolific he was, okay? In 1979, I think, 78, 79, 70s, 70s, there's a maths magazine called Mathematical Intelligence, a German magazine, okay? It said to mathematicians all over the world, you know, give us your most favorite or most beautiful formulae, okay? And out of the top 5, top 3 belong to Euler. The top 3 belong to Euler. You know, there was this various ones which, well, you want to come across f minus e plus v is equal to 2, which says if you take a 3D diagram, number of faces, take away number of edges plus vertices is equal to 2 all the time. Every single time it's 2. That's a good formula anyway. But the number 1, the top 1, okay, the top 1 was this formula here. E to the j pi plus 1 is equal to 0. I guarantee if you Google in the most beautiful formula in mathematics, that'll come up. I'll be very, very surprised if that formula does not come up. Very surprised indeed. I haven't asked a question. Are you going to make a? Are you going to answer the question which is forthcoming, or are you going to make a comment?
I don't know what the forthcoming question is.
Sorry?
I don't know what the forthcoming question
I thought you. Okay, what are you going to say then? Go ahead.
How do they determine what's beautiful?
Well, Mathematical Intelligence is a magazine which. I'll tell you what's so good about this. If that's what you want to know, why is this the most sexy formula in mathematics. You know, if that's what you want to know, I can tell you that. I'll answer that question in a second. If you know. Sorry? Something, yeah, that's close. Yep. Anything else? Come on, what's so attractive about this formula? Why is it number one? You know. Yep. Sorry?
That's trigonometry.
Yep, it does have. Anything else? Yes, you're right. Yep. That's true. And more than that, yep. More than that.
Well, is it because you can't? Is it because when you've got learned, it's not.
You shouldn't say that. Swear word in my language. Don't
sorry.
say natural log.
Sorry, no.
Ask him what it means, or ask some of the Asian kids what that means. I ain't going to tell you what it means. Well, okay. All right, first thing is, some of you got the idea. First thing is, the five, you know, if you think of the most popular constants in mathematics, you know, you think pi is number one, e is number two, you know, and so on, okay? Euler's constant, okay, it's not there. But look at the numbers. Which are the most important numbers in mathematics, or physics, or engineering, or sciences, whatever? The most important numbers are 1 and 0, because you say x times 1 gives you x. X plus 0 gives you x. Okay? That's why they're called neutral element or the identity element, okay? And then you've got that. And then you've got three important numbers there. E, the second most popular constant. Wherever you look in the maths landscape, okay, you'll find E, or you'll find pi. Okay? And then you find square root of -1. And look at, so the first thing is it brings up five fundamental constants together. You know, who would bring that up? You know, okay? Also, who, if I asked you this question, if I asked you, set this as an assignment, I said, work out this 2.71828, going on forever. You took that to the square root of -1, times that by 3.141592, that goes on forever. Work that out, add 1 to it, and you would get 0. Who would have thought that? Would you have thought that? You know, or forget that, this. You work that number out, this number here, you know, hang on, let me zoom out of this. If you work out this number, take the index square root of -1, times that by that, you'll get -1. Who would have thought you'd get -1? You know, you look at the back of the book, you've got -1. There must be something wrong there. I would think there's something wrong there, but I know it's not, because, yeah, go ahead.
Is that exactly -1?
It's exactly -1. Yeah, exactly -1. It's not, you know, 0.999 or 1.001. No, exactly -1. How do we know exactly -1? And what's it got to do with this? What's it got to do with exponential form? How do we know it's exactly? Let's show us exactly -1. You, why have you got your mobile? I've just told a student off, and then you're sitting there with your mobile right in front of me. I can't believe you have the audacity to have your mobile right in front of the desk and showing it to me. Okay. How do we show it's exactly -1? It's not 0.99 or 1.001. How do we show e to the j pi is exactly -1, or e to the j pi plus 1 is equal to 0? How do I show this? Yeah. All you've got to do is put it in there, pi in there, don't you? Yeah. All you've got to do is put pi in there. So it's cos pi, okay, plus j sine pi. And what's sine pi equal to? Sorry? 0, and that is equal to -1. There you are. You've shown it's exactly -1. You know, like I say, it's one of the most elegant formulae in the whole of mathematics. Okay, what about show that e to the minus j theta is equal to cos theta minus j sine theta. How do we show this? How would I show this? Yep.
Well, maybe if you put theta as minus.
Yeah, exactly. We can write e to the minus j theta as e to the j minus theta, can't we? Yeah. Okay. And then we can, like you said, we can write this as r is 1, isn't it, in this case? So it's cos minus theta, yeah? Plus j sine minus theta, okay? Let me zoom into that. What about cos minus theta? Yes, cos theta, okay? If you go back to chapter 4, you'll find cos minus theta is actually equal to cos theta, okay? Guess what sine minus theta is equal to? Yeah, minus sine theta. So you get cos theta, okay, minus j sine theta. Okay, you're asked to show this and you've shown it. Okay? All right, let's do another example. Let's show, okay, write this number in exponential form, in complex exponential form. That number there. How do we write that in complex exponential form? So, how do we do this? How would you go about doing this? I want to write this in complex exponential form. So, what's the number? It's, the voltage V is 20 times sine 1000t minus, it says minus 30 degrees, that's what it says. This is minus 5, which means it's minus 30 degrees. Okay, yep.
First we convert the 30 into...
Yep, exactly. We've got to write that into, what do you call it, into radians, yeah, solution. Okay, so 30 degrees. What is that in radians? You know this one inside out. Yeah, pi over 6, yep, pi over 6, well done. Pi over 6. So we can write V is equal to 20 sine 1000t minus pi over 6. Okay, but how do we, I want to write it in exponential form. What's the nearest exponential form I can get? Go on then, Thomas.
Closer to more like just...
Sorry?
Would it be just like the 20 exponential form?
It'd be 20, yeah, let's just try that. It'd be 20 e to the j what?
J...
Sorry?
J 1000
Yeah.
t
1000
minus
t
pi over 6.
minus pi over 6, okay? Now if we write that out, if we work this out, okay? If we work this out, what do we get? We get, what do you get? 20, what do you get? Now you should be able to convert that. What do you get? Let's see if this is equal. We want this. What do you, if you do this, what do we get? Come on, I've done it, you know, when you lot were stuck last time, yeah?
120 cos.
Yeah, cos of that argument plus j sine of that argument, isn't it? Yeah. So cos 1000 t minus pi over 6 plus j sine 1000 t minus pi over 6. Yeah. Okay. If you take the 20 in, what do you get? You get 20 cos 1000t minus pi over 6 plus j20 sine 1000t minus pi over 6. Now, if you look at that, what do we need? It says V is equal to that thing there, isn't it? Yeah, that's it. But we've got it down here, haven't we? So we need to pick up that. We need to throw away the 20 cosine, don't we? Yeah. We want to pick up the sine, and we want to throw away. We want to throw that up. We want to select this one. So how do we select? Because if you put 20, Thomas just said we want to have 20 each, and I agree with him. We're more or less there. But the problem is we want only the sine. We don't want the cosine.
1000 minus 0.6.
No. Go ahead. Sorry? It's what?
You sub in the value of...
No. Go on.
I was going to say that inside could make that pi over 2.
No. Go on,
Could
Patrick.
you just maybe try and pick out the imaginary part?
Exactly.
Or something like that?
Yeah, that's what you do. Obviously you do. Obviously you do. You've got complex number, got two parts. Okay, real part and the imaginary part. This is the imaginary part, isn't it? So you just pick out. So in order to throw the other one away, in order to throw that's the real part, you want to throw it away, don't you? Yeah. Throw that away. The only way you can do that is if you write this as imaginary of 20e to the j 1000t minus pi over 6. Okay, that in turn that would pick up this one, isn't it? Wouldn't it? Yeah, the imaginary part. Yeah. Remember when you have a plus jb, the imaginary part of a plus jb is b, isn't it? Yeah, that's what you get, don't you? You get a plus jb, and I said put im in front. That means pick up just the number next to the j. That's what we want to do. We want to pick up the number next to the j here, don't we? Okay. All right. So remember that. I know we did that last week. I know that was pretty straightforward, but you've got to be able to use that. So that's the imaginary part of that. De Moivre's theorem says in exponential form. So R, we've got Z is equal to R. Let's use De Moivre's theorem in exponential form. Exponential form. What's going to be the formula? Again, nothing exponential to remember. You put down Z is equal to R e to the j theta. What's Z to the n going to equal? What's the great advantages? What's it going to be? If you want to work out Z to the power n, what's it going to be? Go on then,
It's going to
Patrick.
be R to the n,
Yeah.
then E to the j, then n theta.
Yeah, exactly. Nothing to remember, is there? The way, if I ask you to work out, 2x to the power of 5, you'll say 2 to the power of 5, x to the power of 5. Same thing. Okay? So that's the way you do those, yeah? And they're also used in oscillations, so you can have a look at that simple harmonic motion. You find complex numbers cropping up in oscillations. Now, like I said, the most important thing here is just to remember that if you want to put it in polar form, it's got great advantage, but you've got to recall that it must be in exponential form. I mean, in radians. The argument must be in radians. Okay, once I